So before going to singularity, let us recall what is Taylor series, Lorenz series, etc. Okay, so I will define what is Taylor series. So we studied Taylor series. That means for a function f of z, if function f of z is analytic at z equal to z naught, then f of z can be represented as f of z is equal to sigma n equal to 0 to infinity an z minus z naught all power n. And for if an is equal to f nth derivative of z naught divided by n factorial, and this series is called Taylor series of a function f of z, and this is valid. Okay, so Taylor series of a function is valid, and what is our center? Center is z naught, and it is valid in a circle mod z minus z naught with radius r less than r. If you take any point inside this circle, the function satisfies series representation, and if you take any point outside, it doesn't satisfy. Such expansion is called a Taylor series expansion. Now, so here the condition is for Taylor series, the function should be analytic at the point at the center z naught, and should be analytic inside the circle. And we know that the series representation is valid only inside this circle. Okay, so now what we done is, if we have two questions, can we represent uh, f of z in terms of series if z naught is f is not analytic at z naught. That means here we have analyticity, the condition f of z must be analytic. And the second question is, can we represent series representation of f of z outside this circle of convergence, that is mod z minus z naught less than r. So these are the two questions, and so we want to develop an series representation for a function which is not analytic at its center. And if it is analytic, then the series representation must be Taylor series. If not, we have to find a series representation, and we have to find series representation of the same function outside circle of convergence. So for that, we define Lorenz series. So what is Lorenz series? So if even if f of z is not analytic at z equal to z naught, so the condition is f of z, if f of z is analytic inside an annular region. So that is annular region is R1 less than mod z minus z naught less than R2. So this is annular region with we have center z naught, and it is not required. Analyticity at center is not required. Even though f is not analytic at z naught, it doesn't matter. So this is R1, and suppose this circle is with radius R2. So the condition is we have the function must be analytic in the annular region. Then then we can represent then we can represent f of z as a Taylor's as a series representation. F of z is equal to sigma n equal to 0 to infinity a n z minus z naught all power n. So here the powers of n is positive. So this is called a Taylor series part, and plus there is another part sigma n equal to 1 to infinity bn divided by z minus z naught all power n, and this part is called a principal part. So this is the another series representation where we can represent any. So this is the answer for both questions. So even though if it's not analytic at z naught, we can represent it as a series representation, f as a series representation, even though it is outside the circle of convergence, or then also we can represent as a series. So now, based on Lorenz series, we will define what are the we will characterize uh, singularities. Okay, so first of all, I will define what is definition of singularity. So a point z equal to z naught is said to be a singular point of f of z if f of z is not analytic at z naught. So if f of z is not analytic at z naught, then the function f of z has a singularity at the point z equal to z naught. For example, so I will give you few examples. So if I take f of z equal to 1 by z, then this function, then f of z is not analytic at ഏത് പോയിന്റിൽ analytic അല്ലാത്തത്? So the denominator becomes 0. Okay, so not analytic at z equal to 0. So here it is not defined, and analytic everywhere. So this point, therefore z equal to 0 is a singular point. Okay, so z equal to 0 is a singular point. Now I will give you another example. You take f of z equal to sin z divided by z raised to 6. So here also the problem is the function sin z is analytic, z raised to 6 is analytic. So sin z by z raised to 6 is always analytic except at z equal to 0. So here f of z is not analytic at z equal to 0. Okay. So such therefore z equal to 0 is a singular point. Now I will give another example. If you take sin 1 by z. So here sin when z equal to 0, this function is not analytic. You can either check or you can directly see. It's not defined there. So then z equal to 0 is again a singular point. And if you take another example, f of z equal to 3 by z minus 5, then here z equal to 5 is a singular point. Okay. Now, so we got or we understand what is singular points, and it's very easy. Now we will classify the singular point based on Lorenz series expansion. So, now how to take Lorenz series expansion of a function which has a singularity at z naught. Suppose the isolated singularity of f of z at z equal to z naught. That means f of z is not analytic at z equal to z naught, can be classified by Lorenz series. So Lorenz series is f of z is equal to sigma n equal to 1 to infinity a n z minus z naught all power n plus sigma n equal to 1 to infinity bn divided by z minus z naught all power n. So this part is called Taylor series part, and this part is called principal part. Okay, so I told you we can represent Taylor series Lorentz series expansion of f of z in any neighborhood. But for classifying singularity, we will take valid in the immediate neighborhood of singular point z equal to z naught, except at z naught itself. So we will take this annular region 0 less than mod z minus z naught less than r. That is, so we will expand series representation of f of z in this annular region. Now, types of singularity. So mainly there are three types of singularity. First one is removable singularity. Removable singularity. Okay, so let us define what is removable singularity. So, so, so we will classify singularity based on Lorenz series. So let z equal to z naught be a singular point of f of z. Then, okay, if the Lorenz series expansion of f of z with center z naught has no principal part, that means no terms in principal part, that is that means f of z must be in the form n equal to sigma n equal to 0 to infinity a n z minus z naught all power n plus 0. And there is no principal part. Then z equal to z naught is called removable singularity. Removable singularity. Basically, that must be a Taylor series. Okay, removable singularity. This singularity can be removed. So, this type of singularity is called a removable singularity. I will give you an example. If you take f of z equal to sin z divided by z. So clearly here z equal to 0 is a singular point, right? Because it's not defined there. Sin z by sin 0 by 0, it's maybe 0 by 0. So it's not defined there, therefore it's not analytic. So everywhere else it is analytic, because sin z is analytic everywhere, z is analytic everywhere. Therefore rational function must be analytic. So here the only point of singularity is 0. Now we will find the immediate Lorenz series expansion. So series expansion. So same set. So already we know that what is the Maclaurin series expansion of sin z. So sin z is 1, sorry, z minus z cubed by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 by 7 factorial plus etc. And this is valid for mod z less than infinity. So this is valid everywhere except z equal to 0. So now, now, now what is the Lorenz series expansion of Lorenz series expansion of sin z divided by z is equal to 1 by z into, we will expand this, z minus z cubed by 3 factorial plus z raised to 5 by 5 factorial minus etc. Now we will check what will be the series expansion. If you multiply this, 1 minus z square by 3 factorial plus z raised to 5 by 5, sorry, z raised to 4 by 5 factorial minus etc. So what is the representation? Sigma. ഇതെങ്ങനെ എഴുതാം? Sigma n equal to 0 to infinity minus 1 power n z power 1 0 there, right? Z power n minus 2n divided by 2n plus 1 factorial. Okay, so this is valid when mod z less than infinity. So n equal to 0, then 1, and n equal to 1, then 2 minus 2. Okay, correct. So this is the Lorenz series expansion of sin z by z. So there is no principal part, right? So the principal part is absent here because all powers of z is positive n, positive powers of n. So here principal part is 0, therefore z equal to 0 is a removable singularity. Now you can write another example. If you take f of z equal to e raised to z minus 1 by z, here also you will get removable singularity. You just practice. Okay. So if the Lorenz series expansion has no principal part, then the singularity is called removable singularity. Now I will define the second type of singularity. It's called pole. So this is very important. So pole. So what I will define what is pole. Let z equal to z naught be a singular point of f of z if Lorentz series expansion of f of z with the center z naught has only, in the first case there is no principal part, and second case has only finitely many terms in principal part, then z equal to z naught is a pole. The singularity is called pole. That is the Lorentz series expansion of f of z is of the form sigma. There is a Taylor series part, sigma n equal to 0 to infinity n z minus z naught all power n plus. Now the principal part has p1 by z minus z naught plus p2 by z minus z naught square plus etc. bm z minus z naught all power n. So here how many terms in the principal part? Only finitely many. Okay, only finitely many. So therefore z equal to z naught is a pole. So singularity is a pole, and we can define the order, pole of order m. So what is order of a pole? It is the highest degree of z minus 1 by z minus z naught. So here the highest degree is m. Therefore z equal to z naught is a pole of order m. Now we will give we will do an example. If I take f of z is equal to sin z divided by z raised to 4. So now what is the Lorenz series expansion? So what is the singular point? Z equal to 0 is a singular point. Right? It's not defined in 0, even not defined in 0. Therefore z equal to 0 is a singular point. Now we will find Lorenz series expansion with the center 0 of sin z divided by z raised to 4. So this is 1 by 4, z raised to 4 into sin z. Expansion is z minus z cubed by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 by 7 factorial plus etc. And this is valid. This is valid when 0 less than mod z less than infinity. Okay, now we will define. Okay, so this is equal to 1 by z cube minus 1 by 3 factorial into 1 by z plus z by 5 factorial minus z cube by 7 factorial plus etc. So here all Taylor series part, right? Because here all powers of z must be positive. Then as goes on, it is positive. Now what is the principal part? So this is the principal part. So how many terms are there? Only two terms. So this is a only finitely many terms in the principal part. Therefore, z equal to 0 is a pole of order. What is the order? Highest degree of z minus 0 all raised to n. So here pole of order 3. So if only finitely many elements in uh, finitely many terms in principal part, then we call it is a pole. Now last, so now we will characterize or we will explain what will be the last type of singularity. So third one is essential singularity. So this is the essential singularity. So first removable singularity, principal part has no term. In Paul principal part has finitely many terms. Then obviously for essential singularity, principal part must have infinitely many terms. That are the three categories. So the definition, let z equal to z naught be a singular point. Okay. Then if 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 the Lorenz series expansion of f of z at z equal to z naught has infinitely many terms in principal part infinitely many terms in principal part, then z equal to z naught is an essential singularity. So essential singularity must have infinitely many terms in principal part. So this is same as sigma n equal to 0 to infinity n z minus z naught all power n. This is Taylor series part plus sigma n equal to 1 to infinity bn divided by z minus z naught all power. Now I will give an example. If I take f of z equal to e raised to 1 by z. So here z equal to 0 is a singular point because it's not defined there, even not defined. Now we will, so already we know that Maclaurin series of e raised to z. What is Maclaurin series of e raised to z? 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial plus etc. Then Lorenz series expansion of e raised to 1 by z is equal to 1 plus 1 by z plus, so this is valid when mod z less than infinity. 1 by 2 factorial 1 all square 1 by 3 factorial 1 by z all cube plus etc. So the powers, so the so this is valid when mod, so this is valid when mod, so this is valid when 0 less than mod z less than infinity. So how many terms are in the principal part? There are infinitely many terms in this principal part. Then z equal to 0 is an essential singularity. So we classified three types of singularity: removable, pole, and essential singularity. Okay.